Hello everyone, I'm Pengfei from Huazhong University of Science and Technology. Today I'm here to talk about the work improving the restore performance via physical-locality middleware for backup systems. In the big data era, the backup system in the data center store a large amount of archival data, such as multiple versions of the software and snapshots of the servers. The backup systems are used for achieving implementation efficiency and version rollbacks, which however contain a lot of redundancy. Take the software of Linux as an example. The software developers update the first version to release the second one, and then the third. When we back up in these versions, few data are different where most data remain the same. Hence, high redundancy exists among different versions. Data deduplication technique removes the redundancy at the data block level, which removes the deduplicated chunks and only stores the unique chunks to achieve high storage efficiency. Hence, data deduplication is widely used in the backup systems. A common deduplication system contains two phases, including deduplication and restore phases. In the deduplication phase, the data stream is firstly divided into chunks with on average 4 to 8 kilobytes via the chunking algorithms. Each chunk is represented as a 20-byte fingerprint. Two chunks share the same fingerprint are identified as duplicated chunks. To accelerate the deduplication phase, we maintain a fingerprint cache in the memory. However, we need to search the full fingerprint index table on disk when the coming chunks miss the cache. Next, the identified unique chunks are stored in containers for archiving, which group the chunks together. At the same time, we record the chunk list in a recipe for restoring the original data in the future. The data needs to be restored from system crashes or version rollbacks. In the restoring phase, we first access the recipe to determine which and where to restore the original chunks, and then read the real data from different containers to assemble the original data stream. However, the deduplication system has two challenges. The first challenge is chunk-based access bottleneck. For example, indexing 4 TB data requires 20 GB indexes, which are hard to be put in memory. Therefore, search and prefetch between the disk and memory incurs high I/O overhead. Existing schemes leverage non-exist deduplication algorithm to improve the deduplication performance, which however degrades the deduplication ratio, since they don't search the full index table on disk. The second challenge is the chunk fragmentation problem. During the deduplication phase, the unique chunks are stored in different containers, where the duplicate chunks are not stored. As a result, version 1 is stored into 3 different containers. Follow the same process, version 2 and 3 are respectively stored into 5 and 6 containers, indicating that the data are highly fragmented. Moreover, the chunk fragmentation issue is exacerbated over time, which leads to low restore performance. Existing schemes such as caching and rewriting either fail to achieve high physical locality or degrade the deduplication ratio, which are inefficient when there are more and more backup versions. Unlike existing schemes, we explore the access pattern of the chunks and propose HiDeStore, which achieves high deduplication and restore performance without degrading the deduplication ratios. We conduct a heuristic experiment to figure out the chunk number distribution. In this experiment, we tag the chunks with the version IDs, and the tags are updated when the chunks are contained by the new versions. As a result, the tags represented the chunks are recently contained by which versions. We observe that the chunks not appearing in the current version have a low probability to appear in the subsequent versions, which are called code chunks. In our work, we leverage this observation to classify the hot and cold chunks by only searching hot chunks and storing the hot chunks together. We improve the deduplication and restore performance. Compared with existing schemes, our overall architecture contains 3 main components, including a fingerprint cache, a chunk filter, and a new recipe store. The fingerprint cache is used to identify the hot and cold chunks. We maintain 2 hash tables in the fingerprint cache, which respectively store the cold and hot chunks. The chunks which hit the cache or first appear are hot chunks. All chunks can be classified into 3 cases during processing. In case 1, chunk A meets the cache and is identified as a unique chunk. We insert its metadata into T2 and store its data in an active container. In case 2, chunk B hits T1 and hence is identified as a duplicated hot chunk. In this case, we remove the metadata of B from T1 and insert the metadata of B into T2. We don't need to store the data of B since it has been stored before. In case 3, we do nothing since chunk C hit T2, which is identified as a duplicated hot chunk. Meanwhile, the data of chunk C has been stored into the active container. After identifying the hot and cold chunks, we classify and separately store the different chunks. By storing hot chunks in active containers and moving cold chunks to the archival containers. Moreover, we identify the sparse containers by calculating the container utilization during the chunk moving. We also merge and compact the sparse containers to improve the space utilization. Finally, we update the recipe to guarantee that the original data can be correctly restored. Instead of updating all recipes, we only update the previous one to avoid the high overhead. As a result, all recipes form a chain, which will be further updated during restoring. We evaluated our scheme on a Linux server with 4 widely used backup datasets. Our evaluation results show that our proposed scheme achieves competitive deduplication ratio with the exact deduplication schemes, since we improve the fingerprint cache efficiency over existing schemes. By only searching the hot rather than all chunks, our scheme incurs low overhead to search the indices during the deduplication phase, and hence improving the deduplication performance. Moreover, we also improve the physical locality for the new backup versions and hence improving the restore performance. As a conclusion, our work focuses on the fragmentation issue in the deduplication system, and we identify and classify the hot and cold chunks according to the storage locality. Our evaluation results show that our scheme achieves a performance trade-off among deduplication performance, restore performance, and the deduplication ratio. More details and evaluation results can be found in our paper. We also release our codes for public use on GitHub. That's all. Thank you.